Hello all of you. Today we are going to discuss another complex topic of our series, that is ripple counter, and these counters are also known as asynchronous counter. This is one of the very complex topic in the digital system design subject that we are generally study in the third semester. So the ripple counter, as the name suggests, it works on the ripple of one another, like as we see the waves that is going over the on the water. There is kind of ripple that the previous wave is going to transfer the power to the next wave, so that the wave can proceed in a particular direction. The same In the same way the ripple counter work, the output of the first flip flop performed as the input of the another flip flop, so that a ripple is going to be passed from one flip flop to another flip flop, so that these counter can work. Now, first of all, we distinguished between different counter with the help of these mechanism. There is mainly two type of counter, that is synchronous and asynchronous counter. Synchronous counters are those counters in which the clock pulse, that is, let's suppose this is a 3-bit counter, and these are the flip flop that we are going to be using the counter. So if the clock pulse are synchronized in on the flip flop, then this kind of counter is known as asynchronous counter or parallel counter, because the processing is parallel. All the flip flop get the input in a single clock pulse. They work parallelly and can produce the output parallel. So these counters are very fast and it is synchronized with each other. That's why it is known as parallel or synchronous counter. While in case of the another counter in which the clock pulse is not going in a synchronous manner, but in going in a ripple manner, like this. Again, take the same example, 3-bit counter. We have the clock input, and the clock is input to the first one, and the output of the first flip flop can perform as the input clock of the second one over here, and like this. So the output, the input is going like this. This is in the form of ripple, and it can produce the output after the 3 clock pulse, because the first clock pulse can make this circuit only works. In the second clock pulse, these 2 circuit can work, and in the third clock pulse, these 3 circuit can work. So in these counters are work in a ripple cases and can produce the output after the 3 clock pulse. So these counters are known as a ripple counter or asynchronous counter, where because there is no synchronization between the different input clocks. So the ripple counters are generally slow counter at perform in a serial manner, while synchronous counter is a very fast counter at its work in a parallel manner. There is no synchronization in case of clock in the ripple counter, while there is a proper synchronization of the clock, and the clock is going to be at the same time in all the flip flop. That's why it is known as parallel or synchronous counter. So these are the classification of these two counters. Now another thing is that now what is counter? The counter is nothing but it can use, as the name suggests, it can use to count a certain things. In case of digital circuit, they can count the digital input pulses. Digital input pulses is nothing but the clock that is going to be input. So the counter is nothing but a circuit that can use to count the number of the pulses that is coming into the counter with the help of counting mechanism. Two type of counters, synchronous and asynchronous counter. We are going to focus on this ripple counter in this lecture. The ripple counter allows some flip flop output to be used as a source of the clock, as we can as I explained in the previous slide, that one counter's output is performed as the clock of the another counter, while in case of synchronous counter, all the flip flop get same clock pulse. Asynchronous and ripple counters. So it is also known as asynchronous counter because there is no synchronization between input clock, and it's also known as ripple counter because the output is rippled from one flip-flop to another flip-flop. The drawback is the commutative delay is very large, so that these counters are generally slow. There is another thing, that is n flip-flop is required, or we can say the module. The module is nothing, mod of the counter is nothing but the number of state that the particular counter can perform. Like if is this small n is equal to 3, then it can perform 2 to the power 3, that is up to 8 clock pulse. Then in this case we can say that the mod of this counter is 8 or 2 ki power 3. So this number 8 is nothing but the number of state from that a counter can pass. Like in case of 3 input, let's suppose the input is x, a, b and c, and the output is 0 0 0 first state, second state is 0 0 1, third is 0 1 0, and up to 8th state is nothing but that is 1 1 1. There is a difference between the decimal output and a state. This is the state that is starting from the first, and the first one is 0 0 0, that is 0 decimal equivalent is equal to the state number 1. So the decimal output is from 0 to 7 only, but the state is from 1 to 8 only, and this mode number is nothing but the number of state. So that we can say that for m is equal to 8, we have the 8 number of state from 0 to 7. So that is the difference between the number of the count output and the number of the state for a particular counter can perform. The output of the last flip-flop, that is the MSB, divide the input clock frequency by the mode number of the counter, and hence a counter is also known as frequency divider. This is also known as frequency divider. This ripple counter is also known as frequency divider because the input clock pulse of the first can perform multiple time, while the last clock pulse after 3 or 4 flip-flop it can decrease the frequency 1 and 1, as we can see in the earlier example as well. That the frequency is going to be, input clock frequency is going to be divided as we go out in the ripple form from one flip-flop to another flip-flop. So this is the JK flip-flop. The one of the problems, or we can say one of the thing that we have to understand, that by making synchronous counter we have to use only 2 flip-flop, either T flip-flop or JK flip-flop. Why this happen? Because in the ripple counter we can use the toggle condition of the flip-flop, and the toggle condition is exist only in the toggle or in the JK flip-flop. So ripple counter can be manufactured or can be made by use of T flip-flop or JK flip-flop, and especially by using the toggle condition of D and JK flip-flop. So this is the JK flip-flop, as we can see over here with the help of NAND latch, and this is the truth table of the JK flip-flop. Here we can see for clock input J 0 0, we have the output QT, that is known as no change. For 0 1, this is 0. For 1 0, this is 1, that is set, and for 1 1, there the output is toggle. This toggle means that the whatever the previous state, the next state is nothing but the opposite of the previous state. So let's suppose if JK flip-flop at the output is equal to 0 at a time t, then after the arrival of the clock pulse over here at time t plus 1, the output is flipped to 1 if J and K input are 1 and 1. It may possible if this is 1 at time t is equal to 0, then for t is equal to 1, it is equal to again flipped by the digit, that is 1 is going to be t plus 1 is equal to 0. So this toggle condition is nothing but it can flip the previous state of the counter. Now this is a 2-bit asynchronous up counter. Up means when the counting is going to be up, that is 0, 1, 2, 3, 4, 5. This is up counting. And there is another counter which is known as down counter, in which the counting is going to be in the opposite direction. Like for 3-bit or 2-bit counter, the maximum output is 3. Then the count is 3, 2, 1 and 0. For the 8-bit, it is 7, 6, 5, 4, 3, 2, 1 and 0. This is for the down counter. Now we are going to study up counter, that is count is positive, that is 0, 1, 2, 3. So we have a JK flip-flop over, one JK flip-flop over here, one JK flip-flop over here. We are going to use 2 flip-flop, so it can perform up to 2 to the power 2, that is 4 state. 4 state means 0, 1, 2 and 3, that is only 4 state starting from 0 to 3 count. So it can perform 0, 1, 2 and 3. So these are the flip-flop. First and foremost condition is we have to put this JK into toggle condition, and for doing this J and K must be equal to 1 in all the flip-flop. So J is equal to 1, K is equal to 1, as we can see over here and over here. So in both the case, these 2 flip-flop are in toggle condition. Then the output of the then the input clock is this, and the output of this clock pulse is going to feed the next flip-flop. As we can see over here, there is a bubble, that means it can generate Q0 only, because it generates Q0 bar, but due to this bubble it became Q0 only. Now this is F0, this is F1. Now if we see the timing diagram, what has happened? Initially Q is equal to 0, this is equal to 0. Now after the arrival of first flip-flop, first clock pulse, what happened? Due to this toggle condition, this became 0, became 1. Then the output is 0, this is 0 and this is 1. In the next clock pulse, this 1 became again 0, and now this output is flipped 0 to 1, then output is 1, 0, and in the final case this is 1 and this is again 1, this is 1, and in the next case again it is flipped from to 0, 0. For we can see also the timing diagram as well. This is the clock pulse and this is the Q0 and Q1, and this is the Q0 bar. So at the arrival of the first flip-flop, initially they are 0, 0. The first one is going from 0 to 1. So this is 1 and this is 0. Now this output is going to feed the next flip-flop. So for Q1, this is the clock pulse. So at the edge of this clock pulse, we can see the output is flipped over here. So it maintains 0 until the positive edge of this clock pulse is not happened. So if this is happened, that this became 1, and in the second positive clock pulse, we have the again 1 to flip to 0. So we have the combination 0, 0, then 0, 1, then 1, 0, then 1, 1, and then 0, 0. So in this way, our ripple counter works. One more thing, there is this symbol. This is known as clock input. So if there is no bubble, then the clock input is positive, means the triggering is happen at the positive edge of the clock pulse, or first edge of the clock pulse, or leading edge of the clock pulse. If it have the bubble over here, then it is known as negative edge triggering. In that case, the triggering is happened at the negative edge of the clock pulse, over here, over here, over here, and over here. So in this way, this is known as negative edge or tailing edge flipping, or ending edge flipping over here. So in this way, a 2-bit asynchronous counter works. Now in case of 3-bit asynchronous counter, there is nothing, just we have to add one more flip-flop to the to make a 3-bit ripple counter, and we have to add this JK to the going in the toggle condition. So all the flip-flop, the first one, the second one, and the third one, all are at flip-flop, all are at toggle condition, and this is the initial clock pulse, and positive edge triggering is over here, and these are the output that can these are the internal connection of the counter. So we can see over here, this is the connection. It can perform the up counting as well. Now what happened if the positive clock pulse appear over here? Due to this, j is equal to 1, k is equal to 1, the output is flipped to 0 to 1. If it is initially it is 0, due to reset we have the output is equal to 1, but there is no change in over here. Due to this, there is no change, no input clock is going over here, so it can maintain up to 0, as we can see over here. And again there is no change over here, so it can also maintain 0 0 over here. So when the arrival of the next clock pulse, it flipped from 1 to 0. Now it flipped from 1 to 0, so there is a change in the opposite of q bar, that is it's going from 0 to 1. So there is a flip from 0 to 1 over here, and it can maintain up to the next flip on the q bar cycle, q0 bar cycle, and it can maintain the until this q1 bar is not going to be changed from 0 to 1 positive. So the count is like this. If we see the count, this is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and in the last case all the flip flop can flip and we have 0 0 0. The cycle repeats itself until the clock pulse is arriving continuously. So this is the same case for 4-bit this time negative edge trigger ripple counter. So again same thing, all the flip flop must have in the toggle condition, that is all the flip flop input of the flip flop j and k must be equals to 1, so that it is in the toggle condition. Clock is arriving. Now this time the clock is negative edge trigger, so all the triggering is happened at the negative edge of the clock pulse, as we can see over here, and the similar processes is happened as we can see over here. So now in this case, first flipping for the q0 is equal to, in the very initial, from 0 to 1, 1 to 0, 0 to 1. This output is now performed as the input of the another one. So at the negative edge of this q0, this q1 changes. At the negative of this q1, this q2 changes, and at the negative edge of this q2, this q3 changes. And we can write the count 0 0 0 1 0 0 1 0 0 0 1 1, and in the same way over here 1 0 0 1 1 0 1 0 1 0 1 1, and in the last 1 1 1 and 1, and it is reset to 0 0 0 0. So in this way a ripple counter, negative edge triggered ripple counter can work. Now there is another thing, that is we can perform up and down counting simultaneously with the help of the JK, with the help of this 3-bit asynchronous counter. So the thing is that for up counting we have to feed the next flip flop with the help of Q output as this. But in case of down counting, if we have to perform the down count, that is from 3 to 1 0, then we have to feed the next clock pulse with the Q bar output, as we can see over here for the negative edge triggering. For the positive edge triggering, this thing is opposite. So we can perform the down counting as well with the help of this circuit, just by flipping the input to the next flip flop. So for this output to the next input, it can perform up counting, and from this case it can perform the down counting. Now with the help of another extra circuit, we can perform both this up counting and down counting by a single circuit with the help of this 3-bit up down synchronous counter. So in this case we can see there is a mode select M that can perform up and down count according to the value of M. So if M is equal to 0, we can see this M is equal to 0 line, and due to this NOT gate, this became 1. So this became 0 and this became 1. So if this is 0, this gate, due to input of 0, this gate cannot work, and due to arrival of this 1, this gate can work. So the output to the next clock is going like this. This is the OR gate. This is the addition of these two OR gates. So if this is 1, this is 0, the output is 1, and the signal is passed like this. So it can perform the up counting according to the previous circuit. Now if our mode select m is equal to 1, so in this case this became 1 and this became 0. So in this case this is not going to work, and this gate is going to be work. So the output is going like from Q bar to this input. So now the output input of the next flip flop is coming from the output bar of the previous flip flop, so it can perform the down counting. So just by selecting this mode signal m is equal to 0 or m is equal to 1, we can perform the up and down counting for the 3-bit asynchronous counter in this manner. We can also able to add different number of bit, like this is 3-bit counter because there is only 3 flip flop. For 4-bit counter, we can add one more flip flop over here. For 5th bit, we can add one more flip flop over here. So in this way, we can increase the number of bit of the counter as well. In the last case, we have to, if we want to run the counter for a particular number of state, not for all number of state for which it is designed. So for doing this, we can have an output y over here. So if we want to run this counter up to, let's suppose mode 5, that is this counter can perform up to mode 5. So mode 5 is nothing but from 1, 2, 3, 4 and 5 states. So up to 4, 0 to 4 count. So now in this case, we have an output y is equal to 1 variable. Put y is equal to 1 over the state which we want, and over 0 over the state which we do not want, and make a K map in terms of output of the different flip flop, and we have the output y is equal to this. So now this y is equal to can implement with the help of simple logic gate, and input are coming from the different output of the flip flop. Now as this state is reaches, this output became 0, and this 0 is going in the clear input of different flip flop, and due to this clear input, as this 0 arrives, all the flip flop are reset to its initial condition 0 0 0. So the counter is not going to read the state 0 0 0 1 0 0 1 1 1 0 and 1 1 1. It directly goes from this state to reset to previous state. So in this case, a mode n counter work where we have a valid output and invalid output, and we can reset with the help of this reset logic for which the state we want. This is if we have a sequence that is given, we can also make the same logic, that these states are not wanted and these states are wanted. Having 1, we can perform this y output, and this y output is given to the different CLR input, so that we can perform this state diagram as well. So thank you for the session for this ripple counters. These counters are generally used in different digital clocks and different digital circuits, like in the software of any lift and many digital circuits like digital watch. And this is all for that today.